All right, let's jump right in. Today, we're going to tackle a classic physics problem. But this isn't just about finding the right answer. This is about learning the strategy, how to think like a physicist and break down something that looks complicated into a few really simple steps. Let's get into it.
You know that feeling, right? You've memorized all the formulas, you think you get the concepts, but then you stare at a new problem and it feels like there's some secret handshake you just weren't taught. Well, I'm here to tell you it's not a secret trick. It's a way of thinking, a strategy, and we're going to build it together right now.
So what's the very first thing a physicist does? Before we even think about writing an equation, we just stop. We take a breath, and we break the problem down into its pieces. We're going to deconstruct this puzzle.
Okay, here's our challenge. Let's read it carefully. A body of mass m with a small disk of mass m on it rests on a smooth horizontal plane. The disk is set in motion horizontally with velocity v. To what height h will the disk rise after breaking off the body m? Friction is absent. Now, did you catch those keywords? Smooth horizontal plane and friction is absent? These are not just details, they are massive clues. The problem is practically screaming at us about which physics laws we need to use. Now, the next step is to translate this from English into, well, physics. We list out everything we know, the masses, m, and that initial velocity v. We clearly state what we're looking for, the height h, but most importantly, we write down those conditions. A smooth plane means no external horizontal forces. And no friction, well, that's pretty direct. Just getting organized like this is seriously half the battle. It clears the fog.
All right, with the problem all laid out, it's time to open up our conceptual toolbox. Those conditions we just wrote down, they're going to tell us exactly which tools, which fundamental principles of physics are the perfect fit for this job.
And tool number one is the conservation of momentum. That little phrase, smooth plane, is code. It tells us that in the horizontal direction, there are no outside forces pushing or pulling on our system. And that means the total amount of horizontal oomph, the momentum, of our disk and the body together has to stay exactly the same from the very beginning to the very end.
And here's tool number two, conservation of mechanical energy. The problem handed us a gift when it said friction is absent. That's a huge green light. It means no energy is going to be wasted as heat. Every bit of the initial energy of motion is just going to get converted into other kinds of energy, like potential energy when the disk gets higher.
So, do we have to pick just one? Absolutely not. This is the core of the strategy. We're going to use both of them. They're a team. Momentum is perfect for figuring out what happens with the velocities during the interaction, and energy is perfect for connecting that motion to a change in height. They work together beautifully.
Okay, we've got our tools. Now it's time to actually use them. And to do that, we need to be super clear about our before and after snapshots. The before state is easy, right? It's just the disk moving with velocity v. But what about the after state?
I want you to really visualize this. The little disk slides up, it launches off the body, and it reaches its highest point. What is happening in that split second? What do we know for sure about its motion right then and there? This is the key. This is the big aha moment. At its absolute peak, the disk has stopped going up, so for that one instant, its vertical velocity is 0. But it's not just hanging there, it's still moving sideways. And since there are no external horizontal forces, the disk and the big body m must be moving together horizontally with the exact same velocity. For that instant, they're like a single object cruising to the side. Okay, let's put that first tool to work. Before anything happens, all the horizontal momentum is in that little disk. It's just its mass times its velocity, mv. Now, in our final state, at the peak height, the combined mass, m plus m, is moving together at some new speed. Let's call it v final. Because momentum is conserved, those two things have to be equal.
And just look at that. This is the power of conservation laws. All the messy, complicated forces while the disk was sliding up the ramp. They don't matter. We just linked the beginning state directly to the final state with one clean, simple equation. We now have a way to find that final velocity.
Fantastic. So, we've used momentum to figure out the final horizontal motion. Now let's bring in our second tool, conservation of energy, to connect all of that to the height. Let's follow the energy. In the beginning, all the energy is kinetic. It's all tied up in that moving disk, 1/2 mv squared. Now, in the final state, where did that energy go? Well, some of it is still kinetic energy, because the whole combined system is moving sideways at v final. And the rest of it, it was used to do work against gravity, to lift the disk up. That's its new potential energy, mgh.
And because there's no friction, not a single drop of that energy was lost. The energy just got redistributed. The initial kinetic energy has to perfectly equal the sum of the final kinetic energy and the final potential energy. What we started with, we have to end with.
We have officially done the physics part. We've set up two powerful equations based on two fundamental laws. Now for the really satisfying part, we get to do a little algebra and combine them to find our answer for h.
Here's where the magic happens. Remember our momentum equation gave us a nice expression for V final? Well, our energy equation also has V final in it. We can just take the first expression and plug it right into the second one. This one simple move gets rid of V final and leaves us with an equation where h is the only thing we don't know.
And boom, there it is, the maximum height, h. And take a second to look at this answer. It's not just random letters, it tells a story. The height depends on the initial kinetic energy, but it's scaled by this ratio of the masses. That makes perfect sense. If the big block M is super heavy, it barely moves, and most of the energy can go into making the disk go high. If M is light, it recoils a lot, carrying away a bunch of kinetic energy, so the disk can't go as high.
So yeah, we solved the problem. But the real win here is building a strategy that you can use again and again. Let's wrap this up by packing what we've learned into a little problem-solving kit, starting with the common mistakes that this strategy helps you completely avoid. It is so easy to forget that the big block M is also moving at the end, which means it has kinetic energy too. Or you might assume the disk just comes to a complete stop at its peak. Our approach, by always thinking about the entire system and only focusing on the initial and final states, helps us sidestep all of those traps. We just leapfrog over all the complicated stuff in the middle.
So here it is, your takeaway kit. 1. Deconstruct the problem. 2. Identify your whole system. 3. Hunt for those clues, smooth surfaces, no friction, that tell you which quantities are conserved. 4. Clearly define your before and after snapshots. And 5. Let the conservation laws build the bridge between them. This isn't just for this problem. This is a blueprint for so many problems in mechanics. And I'll leave you with one last thing to think about. What if the problem wasn't so nice? What if there was friction between the disk and the body? Which of our powerful tools would suddenly become useless? And how would that change our final answer for the height? Thinking through questions like that is how you go from just solving problems to truly understanding the physics. Thanks for joining me on this one.